Okay, everybody, can you see my screen?
Yes, Dr. Ali.
Yes, Dr. Ali.
Okay, great. Um, as you remember that in the last class, we are discussing various questions and numerical problems about that inertia constant. So in continuation to those, there were some questions, I think that we were ran out of time. I could not cover. So first I like to discuss those questions and then we will start the new topics. Uh, everybody say, let me make it a bigger font. Yeah. Everybody see on question, considered in the following power network, you want to connect an induction machine based wind generator at bus number 6. This is bus number 6. And a photovoltaic system at bus number 5. This is bus number 5. What are the major conditions to connect these renewable generations at those buses? Will the system stability be affected more compared to its present state in case of a major disturbance in the network? So first of all, you see, everybody see this system. This is a pretty standard model. It is called IEEE 9 bus power system model. Like if you just Google IEEE 9 bus, you can see this picture. Sometimes you might see in a little bit different format, but this is the pretty standard model. Very, very well-known model. The power researchers all over the world use this system, especially for stability and power quality studies. So this is very, very standard model. Now, it is called the 9 bus because you see there are 9 bus. This is, the bus number 2, and this is number 7, this is number 8, this is number 9, this is number 3, this is 5, this is 6, this is 4, and then bottommost it is called infinite bus. This is number 1. In that way, because there are 9 buses, accordingly it is called IEEE 9 bus. Sometimes it is called, you will find in the literature, IEEE 3 machine system. IEEE 3 machine system means this is one generator, this is second generator, and infinite bus is treated as a third power source. So you know the definition of infinite bus, meaning that the frequency and voltage at this bus almost constant within a certain limit. This means that whatever load you connect, the voltage and frequency will remain the same within a certain limit. So, and then sometimes it is called 2 generators infinite bus system. And then more frequently it is called 9 bus system. Now, knowing much more about this system, you see this generator and this generator, those are the synchronous generator. Those are the conventional synchronous generators. Those are not any wind generator and of course not the solar system, conventional generator. And then you see this symbol is transformer, this symbol is transformer, there is another transformer, 3 transformer. And then these are the transmission line. These lines are the transmission line. Voltage on those lines are 20 kV. I think I did not mention here, but if you Google, you will see this system, 20 kV. And then those represents the line parameter, like resistance, reactance, and then line charging. Yeah. Now, these all are the transmission line. And can you see some symbol like this rectangular box or circular, sorry, square box? Those are the circuit breaker. So I have written on CB. CB means circuit breaker. This means in real line, at regular intervals, there are circuit breakers. There are circuit breakers. I mean, in everywhere, I did not show, but I am just showing in these places. Now, based on this condition, of course, you can understand that. So there are a couple of things. You see F1, F2, F3, F6, F5, and here F4. Those represents the fault point or fault location. I mean, it could be any other places also, here, there also, but these 6 points are defined: F1, F2, F3, F4, F5, and then F6. Those are the fault location. So this means that if there is any fault at any of those locations, I mean, whatever the type of the fault, three-phase short circuit, three-phase ground, two-phase to ground, or line to line, or single line to ground, there will be stability issue. Stability issue means you will notice that the bus voltage at all locations are not the same. They have been deviated from their normal operating condition. Same thing, the generator terminal bus voltage will change, their speed will change. I mean, of course, because as I said, because these are conventional generators, they have the shaft system. I mean, shaft system is not shown in the picture, but you have to assume that shaft is connected with the help of the turbine prime mover. So therefore, when there will be any fault at any of the locations, then the speed, frequency, voltage, everything will be changed, meaning that their stability will be affected. That is the normal feature of this system. Now, what is the question? Now come back to the question. In the following network, you want to connect an induction machine-based wind generator at bus number 6. Here at this bus, for example, we are connecting a wind generator and a photovoltaic system at bus number 5. Here we are connecting a photovoltaic system. I mean, that can be valid for any place. You might connect here, you might connect here or there. So just I have chosen two locations. Wind generator is here, solar system is here. The first question, what are the major conditions to connect those renewable generation sources at those buses? How will you connect? Will you just inadvertently connect without considering anything? Or there are some considerations? You must first take into account these points, these variables that should be taken care of before connecting. Okay, I assume that, okay, you fulfill those conditions, you properly connect. The next question is, will the system stability be affected more compared to its present state in case of a major disturbance in the network? Now assume that, considering including that wind and solar system fault happened at F1, F2, or whatever the point is, it's a major disturbance. I mean, either 3SD fault, at the least it could be single line to ground fault. Whatever the fault, will the system stability be affected more as compared to its current situation? That is the question. So everybody, do you understand the context of the question?
Yes, Dr. Ali.
Yes, I mean, what is the answer that we are coming that point? First, like understanding the question, that what is being asked in the statement. So the thing is that, as I mentioned, due to any fault, any type of fault at any of these locations, definitely stability issue means definitely voltage, frequency, generator speed will be changed, will be deviated. That is the stability issue. System might not go fully unstable, it might not be fully stepped out or fully pull out, but at least you can say there will be instability issue, meaning that voltage will oscillate, frequency will oscillate, power will oscillate, everything will be oscillating, and then at some point it will be settled down. Yeah. This means system stability will come back later. Now, once you connect the wind generator here and this one, so what is your guess? Does wind generator look, the very first sentence, an induction machine-based wind generator? So you are connect an induction generator here. Now, if the fault happens at any of the locations, whatever F2 point, F3, F5 point, that is fine. So what is your guess? What will happen? I mean, including the induction machine, will the system stability be more worse, or it will be improved, or what will happen? So what is your guess and what do you think? Keep in mind that these are the synchronous machine. G1 and G2 are the synchronous machine. And based on that, the system might come back to normal condition. But if we connect a wind generator that is induction machine based, so what might happen due to any fault at any of these locations? Will the stability be more worse, or it will be improved, or it will be the same? So what do you think? What is your guess?
It will be more worse.
So what is the reason of that?
Uh, Due to the fault, uh, the induction machine might get demagnetized. Like it needs, for magnetization, it needs direct power from the grid.
Yeah, that is right. What you told so far is right. So what type of power it requires from the grid? What?
Reactive power.
Yes. So yes, that is the point. This means because there is one induction machine connected here, I mean, it does not matter it is here or here. I have just assumed it is here. So it will start drawing more and more reactive power from the system. And because it will be drawing more and more reactive power from the system, voltage will be dropping more and more. So therefore, what I am telling, so let me take you to that whiteboard. Uh, so just look on profile, for example, voltage. So I'm drawing the voltage profile. For example, this is the normal condition, and then the fault happened, and of course voltage will go down and come back and oscillate. So assume that this profile is considering the conventional generators, those two generators, G1 and G2 on left side and right side. This is considering SG only. Just keep in mind, if it is, once you connect the IG induction generators, what will happen? It will go down much more. And it might happen that it is not coming back. It might be this situation. Therefore, you might see this profile, this response of voltage, considering those SG plus the IG in the system. It might happen. What is the reason? That thing like Kamana was explaining, because this is IG, therefore before we discussed the induction machine principle is that I'm not explaining the whole thing, just I'm showing you. These are the three-phase coils, for example, A phase, B phase, C phase. It will, from the beginning, it is drawing reactive power. So during fault, what will happen? You see, during fault, voltage has gone significantly low. It is going close. At this point, this is the fault point, F point. It has gone significantly low. And because it has gone significantly low, in case of induction machine, this is the relationship. Its electromagnetic torque is proportional to voltage squared. So this voltage is here, the terminal voltage, Vt, make it Vt. This is the relationship. So therefore you see, because voltage has gone significantly low, consequently your torque will go significantly low. And because torque will go significantly low, so then the power is that torque multiplied by the omega. This is the relationship. So because this will be low, consequently your output power will also go low. Now what this machine will try to do to recover that electromagnetic torque, there is other relationship is that electromagnetic torque is proportional to input current squared, the current here. So this means that because the torque has gone low and then it is proportionate to I square, it will start drawing more current from the system. That thing Kaman was telling. And then drawing more current means drawing much more reactive power. And then you all know the impact or negative adverse effect of drawing the Q. Drawing Q means power factor will be very, very low at the terminal. Consequently, your voltage will be very, very low. So this means definitely you need some sort of control means, transient stability improvement means. We are not discussing that point. We are assuming before connecting any controller, any protection means what will be the situation, what is the stability condition, that thing we are discussing. So therefore during fault condition, what will happen? They will start drawing much more reactive power to compensate that electromagnetic torque. To do that, it is drawing more current and reactive power, much more reactive power. Power factor is going low. Consequently, voltage will be dropped. And it might happen that system is not coming back at all. While it was only SG, synchronous generator, it came back. Can you guess why with the synchronous generator it may come back? What is the feature of synchronous generator that might help it to come back? And what is lacking in the induction machine that it is showing this thing? So what is the basic difference between SG and IG? What is the main, sorry?
Synchronous generator has its magnetic poles.
Yes, it has physical magnetic poles, that is right. And also, I mean, you remember it has the automatic voltage regulator. And also it has the governor control system. You remember one day I was telling, today again we will be discussing those things. So synchronous generator had those two primary controllers, automatic voltage regulator, governor. AVR controls the terminal voltage and governor controls the speed. So that's why there is primary control means. That's why whenever it is trying to go down, immediately those two things are working in case of SG. But in case of IG, those two things are lacking. IG does not have those two primary control. It is dependent on the grid power. That's why that is the thing that Kamana initially told. It will start drawing more reactive power to compensate the reduced amount of the electromagnetic torque. And then the system will be much more, worse and worse. So voltage will go down and even it might not come back. So that is the impact of having the IG in the system. And that is my context to ask that question. So now then go back there again.
So what about the frequency stability? There any effect?
The frequency will go high again, might not come back to the original position. Sometimes it might happen that, for example, if it is United States, then frequency is 60 hertz. After some oscillation, frequency came back, but at 58 hertz or 62 hertz, it settled down. I mean, it is still stability, but might not come back to the original position because voltage has gone significantly low. That is the impact. And even like I drew the picture of voltage, although I did not draw the picture of the active power of the generator. Active power even might go pretty low. I mean, fairly close to zero.
All right.
So this means the answer is, will the system stability be affected more compared to its present state? The answer is yes. And then you have to explain, you have to tell the property of that induction machine. As you explained, that is the property of induction machine. So with the presence of induction machine, system stability will be affected more. Now everybody see, I mentioned that bus number 5 has the photovoltaic system. Now, with the photovoltaic system, there will be some impact, but what is the benefit of having the photovoltaic system? How do you distinguish the photovoltaic versus the IG here? Or what is lacking in the photovoltaic system?
The DC system.
It is that is right. What else? Is there any shaft connected to PV system?
No.
No. You see, this means that the photovoltaic system, first of all, that you said, that's correct. It is DC, and it has no rotating parts. Because it does not have rotating parts, so this means photovoltaic system itself, solar panel is independent of the frequency because it will produce DC and it is static. So there is no question of shaft torsional oscillation or any frequency issue there. I mean, at the connected grid point, there will be frequencies, voltages, but at least impact will not come back until the PV panel because it is AC. And then in between there is, voltage source converter or transformer. Already it is like decoupled. So that's why I'm not bringing that point. I just said this on to make a tricky question. Okay, with the presence of PV and then IG, what will happen? So the IG will be more dominating. That will worsen the system. PV will have some impact at the terminal. I mean, the DC voltage will be a little bit fluctuating, but that will not be a major issue. Main issue will go on the induction machine. So everybody is fine?
Yes, Dr.
Yes. So please note down these points because week after next you will face the midterm exam 1. So again, I will be asking you these similar questions. So I may not ask exactly the same question, but very similar question. That time, like you have to answer. Okay, and then there are first part of this question. See, these are what are the major conditions to connect those renewable sources at those buses? Now, as I said, this is an existing system, and as I told you, the pretty well known all over the world, widely accepted system, this one. So with that system, how would you connect those two sources? Would you just connect or there are some condition that should be made? What do you think? For example, as I said, at each bus, the voltage is 20 kV for this system. It is written here, you see. This is 50 Hertz, 20 kV, 100 MVA base system. This one, it is clearly mentioned. 20 kV. This means at each bus, it has 20 kV. So this means that, for example, it is IG here and then solar system is at this bus. Whatever the output voltage, DC voltage of the PV system, whatever the output voltage of that induction machine based wind generator is, it should ultimately provide that 20 kV. I mean, with the help of the transformer. For example, induction machine might produce only 690 volt, but you have to step up 20 kV. Unless the voltage matches, you cannot connect two systems together. I mean, in other words, this is something like connecting parallel generators. This is one system which has 20 kV. If you want to connect whatever the system is, I mean, a nuclear turbine or gas turbine, another new generator, even this type of generator, is still that must maintain the 20 kV. So voltage must be the same. So that is the meaning. What are the major conditions to connect those sources at those buses? So you would answer that the PV system and then wind generator system should provide 20 kV to connect at this point. Also, what are the conditions? The frequency should be the same. Here it is like 50 Hertz. Accordingly, you have to choose a 50 Hertz system. Otherwise, you cannot connect it here. Also, the phase angle should be the same. For example, at this bus, there is voltage magnitude. It is 20 kV RMS value. Let's say it has phase angle 5 degree. So once you connect that system, that should also have the same phase angle. If there is phase difference, then there will be some sort of circulating current flow from this system to that system or from IG to this system. Consequently, there will be some sort of heat or power loss in the system. Same thing, if frequency does not match, then there will be circulating current. If voltage does not match, there will be circulating current. And that circulating current will cause some loss in the system, gradually overheating, even might be like burnt out at some point. So therefore, that is the meaning of the first part. What are the major conditions to connect those sources? So you would be answering that major condition of that induction machine and PV system. They also must maintain the 20 kV at those buses. They must maintain the same frequency, which is 50 Hertz, and also they must have the same phase as to these buses. Everybody, could you follow me what I said?
Yes, Dr. Ali.
I mean, these are pretty common thing. You all know already. You all know, but then in the context of the questions, again, like you have to remember, revive those things. That's the thing, because those have severe impact on the stability. Without matching the voltage, matching the frequency, phase angle, system will be upset. System will be unstable, because we are dealing with the stability in this class. I am discussing all possible things that are the major causes or sources of the stability. That is the thing. Okay, so assuming that everybody understood this one, then moving forward. Again I am creating complexity to you. Again, the same system, exactly the same structure, but here I am asking different question. Everybody read the question. In the following figure on, consider a three-phase to ground fault occurs at points F1, F2, F3, F4, F5, F6 as indicated. Again, my assumption is that those are the 6 points. Yeah, this is F4. So whatever the fault location is, what I am asking, which fault points would most affect the stability of the generator G1 and G2? Explain your answer. So this means that this is your generator 2, this side your generator 1, and then fault is happening here, 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 and there. Now, everybody keep in mind that, of course, as I early mentioned, these are the transmission line. These are the transmission lines. Can you see some numbers like this plus J and then in parenthesis J? Basically, those numbers are representing the first part is line resistance. Second part is line reactance, X value. And then J value, this is the capacitor value. It is called half line charging. This is the capacitor. You know, at regular intervals along the line, inherently capacitor is built. Those are not any physical capacitor. Just everybody keep in mind, when there is a long distance, long transmission line, at regular intervals, a capacitor is formed automatically due to charging current. Those capacitors are not visible. Those are internal. So that's why the third number in parenthesis, that is representing that capacitor effect. It is called the half line charging. But the first part is resistance, and then these are the reactants. So, and then you see in different line have different numbers. Can you just compare? I mean, the way I have drawn the picture, it looks like this distance and this distance is the same. It is not actually. It depends. It is drawn to look nice, but it is not. For example, depending on the distance, your resistance reactance will vary. Consequently, you see this number different. At each part is all are like different numbers. So therefore, meaning that what I am saying, when the fault is at point F1, you see, this means that is the closest. That is the closest point with respect to distance. Similarly, F2 is closest here. Closest means I'm talking with respect to generator. I mean, this is generator. I mean, there is no distance. In fact, maybe only few meters here. And then this is transformer. Again, this point is pretty close. Maybe this is only a few meters. But then from here to here, there is some distance, and of course there are distance. So therefore, first of all, first question is that, my question was, which fault points would most affect the stability of the generators, G1 and G2? So what I am saying that F2 point is pretty close to generator. F1 point is close to this generator. Then as the distance, as the line increases, the distance from the generator increases. This means F6 point is much further than this point. This is much further than this generator. Similarly, in this side, this point is much further than this point. This is kind of the middle position with respect to this generator, could be almost equidistant, not exactly the equal, but kind of, you may treat. So Do you understand what I am telling? The question was that a three-phase to ground fault happened in any of those 6 points. But the question is which fault points would most affect the stability? So why I am saying that most affect the stability, this means that whatever the fault locations in any of these points, there will be stabilization, definitely. Whatever the amount of the stability level, whatever amount voltage go downside, power go downside, speed increases, frequency increases, whatever the amount is, there will be some impact due to all of these fault points to both generators. But what I am asking, among these 6 points, upon which points will most affect? I mean, which will be most vulnerable? Everybody, do you understand the question?
Yes.
Yes. So therefore, what is your guess?
The closest circuit breaker, I think.
Exactly. That is the right answer. The closer the fault location, the level of severity will increase. So because why? Can you guess why? Because as I said, the distance here and then distance from here to here is different. So with the increase of the distance, which parameter increases? What value increases?
Resistance, I mean impedance. Or
Exactly. Impedance increase. And if the impedance increase, then definitely your current flow will be decreased. Therefore, if you really plot, for example, if you really simulate this system, Manoj, for example, in Omnet or whatever the software is, if you plot corresponding to each fault point, you will notice, and for example, you are looking the voltage profile of this bus and then this bus, you will definitely notice when the fault is here, then this generator voltage is going much more downside as compared to other points. Similarly, when the fault is at F1 point, because this is closest to this generator, definitely voltage will go much more down. Frequency and speed will go much more higher as compared to any other point. Therefore, in that way, as the distance increases, accordingly, there will be less impact. I mean, there will be impact, but less impact. I mean, just take in mind that, for example, something happened in a power plant in Tennessee state, in TVA system. Then the impact versus something happened in New York or Boston area. There might some impact may come because all are interconnected, but very, very little effect, or even might not feel any effect. But if it is in Tennessee state, any generator shut down or two generators shut down, definitely impact will come on the MLGW system. That is the meaning. Because the fault point, disturbance point is closest to us. So therefore the answer would be that F1 and F2 point would most affect the stability. And if the fault is nearby F2, then a G2 generator will be affected most. If fault is nearby this one, this means F1, then G1 will be affected more. I mean, when there is fault at this point, this will be affected more, but this generator will also be affected. But the level of effect is more here, more pronounced here, more dominating here. Similarly, when the fault is at this point, this generator will be affected most than this generator. But this generator will also be affected. And then the amount of effects and how much they will be affected, it depends on their inertia, and it depends on the distance, it depends on their capacity, etc. Everybody, could you follow me?
Yes, Dr. Ali.
Yes. Okay, great. Okay, so now with that moving, and I think you have the first homework set due tomorrow, right? Tomorrow 11:30 p.m. So therefore, I think some of the answer might come from already we discussed this slide and previous slide. I think some of the discussion will come to your answer in that homework number 1, and that is due tomorrow. Okay, now you see, today we will be discussing the few new points. I mean, you all know, but again, extensively, because we are discussing, I mean, stability. We are deeply and deeply looking what are the major governing forces behind the stability in a power network. So we'll be discussing excitation systems, and then prime movers, and then control of active and reactive power, and then numerical problem. Uh, so you all know the excitation system, and then the prime mover. Excitation system means in case of synchronous machine, there are physical magnetic pole. You have to magnetize those. That is the meaning of excitation. I mean, I'm coming in detail. Prime mover means which is the main driving force for a generator, the mechanical side, like turbine, gas turbine, coal turbine, nuclear turbine, steam turbine, whatever. That is the prime mover. So, and then what are their impact? What is their role and what is their impact on the stability? We will be discussing. And what does these two systems do? Control of active and reactive parts. When there is disturbance in the system instability happen, then the main thing is that we have to control active and reactive power. So the thing is that when to control active power and when is the right moment to control the reactive power, or we have to control the both. That is the thing. It depends on the situation. Sometimes reactive power control is dominating. You have to give preference. Sometimes you have to give preference to control active power. Sometimes both. It depends on the situation. So that's why control of active and reactive power is very, very vital, very crucial in maintaining the stability of the power grid. So basically, these are the two powers and these are the two factors that governs the stability. So therefore, now first let's go the excitation system. So what I have written, as I already mentioned, excitation system refers to that magnetization. So in case of synchronous machine, it is magnetization to the physical poles. So in case of the induction machine, that excitation systems comes from the grid in terms of the reactive power. So therefore, here we are focusing on the synchronous machine. Keep in mind, in this slide, our discussion, it is mainly dedicated to the synchronous machine. So therefore, you see what I have written, the basic function of an excitation system is to provide direct current to the synchronous machine field winding. So whatever it is salient pole or non-salient pole, there are physical magnetic pole, and you have to provide DC current to excite or to magnetize that. That is the basic function. In addition, the excitation system performs control and protective function which are essential for the satisfactory performance of the power grid by controlling field voltage and hence the field current. Now, the question is how to excite the field. Field means basically a coil. If you have a magnet and if you if you mount a coil around it, you have to just send the power to the coil. Now, what is the type of that system? One is called DC excitation system, other one is called AC excitation system, and then the third one is called the static excitation system. So therefore, what does that mean? So let me take you to that whiteboard again. Then you will get it. So therefore, let me erase this thing. Okay. So therefore, we are discussing excitation. So just everybody concentrate only on the rotor circuit. So our stator is not the headache. So this is our rotor circuit, and then this is the shaft system. And then we have that physical magnetic pole. For example, we have North Pole, South Pole. And then those North Pole, South Pole, they have the coils around it. They have the coils. They have the coils. Therefore, for example, these are the 2 points. So how to excite those two things? That is the question. So now there are 3 systems. On, you noticed that I showed on is called the DC excitation. So DC excitation means they, because this is the rotor circuit. You all know this is the rotor circuit on which the fields are mounted. So this body is rotating with the help of this one. So therefore the DC excitation means there is a small size of DC generator mounted on the same shaft. This is DC generator, very small size, kind of the battery type of thing. Its function is just to send the DC to the coil, just to send the DC to the coil. So this means DC excitation means there is a small size of, very, very small size of DC generator which is mounted on the same shaft of the rotor. This means that when this thing is moving, these coils together with the DC generator, everything is rotating. That is called the DC excitation. So therefore, all over the world, still there are lots of synchronous machine. I mean, in fact, all power plants still have the synchronous machine. And in many countries, the DC excitation system is prevailing. It is existing. Now, some, power plant, they have the AC excitation. AC excitation means, sorry that I'm the spelling like I'm going the next up. Okay, anyway, so the AC excitation means instead of that DC generator, so the system has AC. On the shaft, there is a small size of AC generator. And that AC generator, and of course, that here it is the requirement of DC. Always keep in mind, for any magnetic field, you must provide the DC to get a steady the flux, to produce a steady flux. That is the DC. Now, because there is a small AC generator, very, very small size, but because it is AC, then definitely you can guess that with that AC generator, there is the rectifier circuit. There is the rectifier circuit. And that rectifier circuit is converting into the DC. And that DC is being supplied to these coils. So therefore, when I'm saying it is AC excitation, meaning that it's a small AC generator together with the rectifier circuit. I mean, everything is placed here in one package. That is called the AC excitation. Now, the third category is that there are some countries or some power location, they don't use neither this one nor that one. They said that, okay, because this is my, let me draw this, sorry, remove these things. They said that, okay, this is my rotor circuit, that is fine, because I have the stator, which is actually producing 3-phase voltage, and I am getting 3-phase power from here. That is my system. I want to use these parts because because this is stator, this body, and that stator is not rotating. So some power engineers say instead of exciting the field from either DC excitation or AC excitation based system, I want to take power from here. This means that the some power is going towards the grid side, and then what you are doing, you are taking some power from all 3 lines. Again, because you see this is the AC system, AC power. So again, you use a rectifier because this is the AC, and then you convert into DC, and then you send that DC power from here to those fields. So now the question is that everybody say, this thing is moving, this rotor is moving, but this side is static. Your rectifier is static, its output terminal is static. So then how it is powering this one? This means that with the help of the brass and slip ring, meaning that this DC system output is, for example, like that. You have to attach a brass, you have to attach a brass or the carbon. Just a moment. These are the brass attached to that, like plus terminal and minus terminal of that DC system. I mean output of the rectifier system. And then this thing is moving. So there are some sort of slip rings. These are called slip ring. So therefore these things are moving with the slip ring, and these brushes are fixed. They are touching the brass. They are coming in contact with the brass. Consequently, the DC power is being supplied to the field system. It is called the static excitation. This system is called static excitation system. Why it is called the static excitation system? Because you are taking the voltage from the static terminal. Because stator is static, it is not moving. Accordingly, it is called the static excitation. Everybody, could you follow me?
Yes, Dr. Ravi.
Yeah. So therefore, three excitation: AC excitation, DC excitation. AC excitation means there is a small AC generator mounted on the same shaft. DC excitation means there is a small DC generator mounted on the same shaft. But static excitation means you are taking the output from the actual generator terminal, you are converting into DC with the help of rectifier, and with the help of the carbon brass and then slip rings, you are providing power to the rotating magnetic field. So that's why now go back there. This is that three system: DC excitation, AC, static. I mean, it's still all over the world, these three systems prevails. And then these days, to avoid these things, easily you can guess that it's complicated and you are dependent on some sources, and then it is incurring some cost. And in case if the system does not work properly, then it will not be magnetized, terminal voltage will be low. That's why in order to avoid this system, these days power engineers are preferring PMSG, permanent magnet synchronous generator, PMSG. So what is the benefit? Benefit is that you don't need any of this system. You can install a permanently magnetized, let's say magnetized for 30 years or 40 years. Time to time you might need some overhauling and some maintenance, but at least those will remain 30 years or 40 years magnetized. So you don't need any of this system. That's why as a power engineer, if you choose to install a generator, for example, whatever the country, definitely you will be choosing the PMSG, not this system. But as I said, still all over the world, this system exists because, for example, 30 years ago, 40 years ago, some generation system was installed or built. Definitely they had this system. Now, even though everybody understands the benefit of having the PMSG, but they are not going to manage this system because it will incur huge cost. It will be a huge loss. And then replacing from this system to that PMSG, it will take some time. It's a money. And then what will happen to the customers? That's why immediately you cannot change it. What I am telling that from now on, I mean, really in the TBA system, there are some new generator based on that PMSG. Therefore, as an engineer, power engineer, if you are asked by someone that which generator system you would prefer today, then definitely the answer would be PMSG, just to avoid these things. And maybe in the near future or in the future, maybe 20 years later, 30 years later, you might see that all over the world, all generators have been changed to PMSG based system. I mean, although of course the wind generator, ocean energy and solar system are increasing, But if you think the conventional sources, then that will be the PMSG, not this type of traditional synchronous generator. Okay, and then now it has that excitation system. Now it has some sort of controller, which is called the governor, sorry, the AVR, automatic voltage regulator. What it does, it controls the DC field. Again, DC field means the dose system, and hence control the terminal voltage, power factor, and reactive power. So therefore, the function of that AVR or automatic voltage regulator system is to control the DC field and accordingly terminal voltage, power factor, and reactive power. So here I think in the next slide, I have a block diagram. So everybody see this picture. This is just a typical example of a power system. It has synchronous generator with 100 MVA. It has a wind generator together with a terminal capacitor, and they are powering to the grids with the help of transformer. Now, because this is synchronous generator, definitely you know wind generator, it does not have any AVR system. It does not have any of these excitation system. You all know that. But this generator has the AVR. So therefore everybody see the last figure, the AVR model. This is the control model. So what does AVR do? The function of the AVR is to watch or monitor the terminal of the synchronous generator. Continuously it is monitoring. Is the voltage going down or is the voltage going high as compared to the rated condition, as compared to the expected voltage here. So that's why you see the comparison. VT means terminal voltage, measured voltage, and VT0 means it is the reference voltage. For example, here you want 11 kV, that is that voltage. And this one is, what is your measured voltage? Is it more than 11 kV or smaller than 11 kV? Has there any fault happened or due to some reason, voltage has been changed? So you see, this is plus, this is minus, meaning that what you are getting here, you are getting difference in voltage. And then there is a, you see, there is a block K over 1 plus ST. It's kind of, you see, very similar to low pass filter, 1 over S plus T. T is the time constant and S is the Laplace operator and K is some sort of gain. So therefore you are passing through that low pass filter and then you are getting some value. And then you see from top you are injecting EFD0. You are injecting some sort of field voltage, some sort of field voltage. So why this is needed? For example, there is no difference in voltage. For example, system is running well. There is no short circuit, open circuit, nothing happened, meaning that there is no difference. So the no difference means then it is zero. So therefore it will be zero. Then ultimate goal field voltage will be zero. But that should not be the case. That's why here you see, always, this means always you need some sort of field voltage to excite those magnet or the field circuit. That's why there is some value. This is a small value, but you need that one. During fault condition, what will happen? Because there will be difference in voltage, some amount will be added so that you can increase the excitation. So that will be your field voltage, and that if you increase the field voltage, meaning that you are increasing the excitation. So you all know the two main condition, two dominating factor or two governing factor behind producing the voltage. One is the flux or the DC field, other one is the speed. That speed comes from prime mover and this field comes, sorry, the excitation or the flux comes from the DC field circuit. That is the function of the AVR. This means you see, ultimately by controlling the DC field voltage, it is maintaining the voltage here. AVR is continuously monitoring in this position. Is there any difference or not? If no difference, then fine. If difference, then okay, take an action. I mean, adjust the field voltage. That's why you see, here it is written AVR controls the DC field. And what it is controlling? It is controlling the terminal voltage. And accordingly, power factor is being controlled. And if you control the power factor, this means you are controlling the reactive power. So you see, when the terminal voltage is low, meaning that is equivalent to low power factor, because there is mass drop in the system. System has some reactive power. That's why controlling the DC field, meaning that controlling terminal voltage. Therefore, you see these three these three variables are analogous: terminal voltage, power factor, reactive power. So everybody keep in mind, these three are analogous. This means if you change this one, these two will be changed. If you increase, those will increase. If you decrease, all will decrease. That is the interrelationship among these three variables. Now, moving forward, come back to that prime mover or the energy supply system. So as you know that prime mover, that is the main mechanical force, main driving factor in a synchronous machine. And that prime mover means basically turbine. Now it can be, I have written here coal-based, oil-based, gas-based, or nuclear energy-based. And how does that turbine runs? How it is? With the help of the fuel. So therefore everybody see, I have written for you, the basic function of the prime mover is to convert the kinetic energy of water as well as the thermal energy derived from fossil fuel and nuclear fission into mechanical energy that is in turn converts electrical energy by synchronous generator. This means that you need some fuel, whatever. In case of nuclear turbine, it is nuclear. In case of hydraulic turbine, it is water. And what they do, they convert either kinetic energy or thermal energy into the mechanical energy. And finally, you get the electrical power or electrical energy. So that's why here are the typical or the standard turbine type, hydraulic turbine. Kinetic energy of water is utilized. Steam turbine, thermal energy derived from fossil fuel and nuclear fission system. Accordingly, name goes. And what is the main function of this system? There is a controller for this system, which is called governor. Governor controls the fuel input to the generator. Now, for example, in case of coal, oil, gas, or nuclear, you need to adjust the generator output or the mechanical input power that is coming from turbine. You need to control those input. If it is coal-based, control the coal. Don't send more coal, or don't give more oil, don't provide more gas. And in this case, don't produce more fission, don't split more uranium and plutonium. That is the meaning. Don't make much more reaction. The governor controls that fuel input. I mean, automatically governor looks the speed and it monitors the turbine system, and accordingly, if needed, it adjusts the fuel input depending on the type of the system. In case of hydraulic turbine, it controls the falling of water. This means it controls the amount of kinetic energy. There is control system with the valve opening and closing. So therefore, see, governor controls the fuel input to the generator and hence control the speed, hence frequency, and hence active power. So these three terms are interrelated: speed, frequency, active power. How? So you all know that, remember that, what is the equation, synchronous speed equation? 120 F over P. Ns equal to 120 F over P. So this means in the speed, there is frequency and pole number. So that's why controlling speed means controlling frequency. And then that is related to active power. How? You all remember that swing equation, phi A equal to Pm minus Pa. This means Pha is your electrical output power, active power. If you control that one, then system will be accelerated or decelerated. And acceleration and deceleration is nothing but the change in speed or frequency. So in that sense, active power control means frequency control, or frequency control means active power control, or speed control means both of these control. So that's why governor can control these three variables. And then you look, the AVR controls the another three variables. In that way, there are total 6 very, very important parameters in synchronous machine that you have to control to maintain the stability. Because in this class, our goal is like we are dedicating to the stability in this course. So we have to make sure that all those 6 variables are at their acceptable position after being subjected to a major disturbance. Terminal voltage, power factor, reactive power, and here speed, frequency, and active power. All 6 points should come back at their acceptable steady state position. If there is any lag, if any component, any parameters does not come back properly, then there will be instability in the system. Either system will be oscillating, might not be fully unstable, but system oscillating, degrading, etc. Shaft is like vibrating, oscillating. You might notice that there is flickering in your bulb, lamp, in some loads, etc. There will be impact. All 6 parameters you have to control. So that's why in case of the synchronous machine, the governor will control these 3 parameters and AVR will control these 3 parameters. And they are interrelated. But it depends the mode of dominance. I mean, we are coming that point later. So everybody, could you follow me so far?
Yes, Dr. Ravi.
Yeah, okay, great. Now, here see that before I showed you that picture, for example, again for the same system, but concentrate on that synchronous generator. This is the governor model. You see, very similar picture to the AVR system. It was the AVR. But see, remember in case of AVR, your input was voltage. You are comparing measured voltage with the reference voltage. And output was your field voltage. Now come back here. In case of the governor system, what is your input? Your input is speed. Because that we learned that your governor system controls the speed, frequency, active power. That's why in the governor model, instead of voltage, here it is speed. Again, this is your measured speed and this is your reference speed. For example, for the synchronous machine, your reference speed is 3000 RPM or 3600 RPM, or if it is hydraulic based, 1800 RPM, 900 RPM, that is your reference. And during fault condition or in any time, 24 hours, what is your measured speed? What speed actually you are getting on the shaft system? That speed will come here. And if there is any difference, that will be progressed through that low pass filter type. Again, in this case, J is some sort of gain, T is time constant, and S is the Laplace operator. And then it is giving you some value if there is difference during any fault. And then what is the main goal of the governor system? Main goal of the control the fuel input to generator. This means you want to control the mechanical power input to the turbine system. That's why whatever the value is coming from here, you have to inject some sort of mechanical power always. And so the final output is the mechanical. This P is the mechanical power. Keep in mind, this is the mechanical power which is available on the shaft system. And that is the main driving force of the generator. So therefore, in that way, governor will control the speed to maintain a power, mechanical power. Now, this governor model, as I showed you, this one and then this AVR model, these are pretty standard model. Now, you all are assigned to present papers. I mean, already Manoj presented. I mean, next class, Kamana present, and you all will be presenting. I think in your paper, you don't have AVR or governor, but if you read literature, if you see many journal articles, conference paper, you will be noticing this standard model, AVR model, and then that governor model. These are pretty standard model which are used to analyze the stability, transient stability. Very often, many authors use these two systems. But in real practice, I mean, this is kind of some sort of standard and simple model. But in real practice, the governor model and the AVR model could be more complicated. For example, this is a system. This is example of large power system model. It has 10 generators, G1, G2, G3, G4, G5, G7, G10, and hugely interconnected system. And you see, the generator on rating 15,000 MVA, and this generator rating is 30,000 MVA. It is called IEG OS 10 machine. This is on like Japanese system. I think, no, it is not written. It is Japanese system. IEG means Institute of Electrical Engineers in Japan, and West 10 machine. They have two systems, East 10, West 10. So West 10 means like in the nearby the Tokyo area. They use 60 hertz frequency, but the eastern part they use 50 hertz system. That's why they have two different systems, East and West 10 machine. And then can you see 30,000 MVA, very big. And this is the swing generator for this system. Now for this type of system, if you analyze this system, then you will see each generator, they have a little bit complicated AVR and governor model. For example, you see AVR and governor. This is that IEG AVR model. You compare the picture I showed you and this one. I mean, goal is to find out the field voltage. That is fine. Your input is voltage. I mean, EA and EAS, those symbol refers to terminal voltage. Here it is written, like reference terminal voltage, generator terminal voltage. I mean, originally I used the symbol like I think here. Originally I used symbol voltage for this model, but because that is on a specific system, and like I have taken these models from their, that standard system. That's why they are using those symbol E, but E means the voltage. And you see what they did in between, they have several structure, several saturation or the limiter. And again, there is on feedback path. So this feedback path was absent in that standard or simple model. So therefore, and then see the governor model, this is somewhat longer. I mean, final goal is to produce the torque or the mechanical power. That is fine. But you see, there is some feedback, and there are some specific thing like 65 M means turbine load reference, 77 M means turbine load limiters. In that way, it is complicated. So therefore, different system might have different model. That is fine. But this, what I am telling that these two, this governor model and this AVR model, whatever the system is, even for you analyze that system, 10 machine system, still you can use this AVR and governor model. It will give you pretty good result, I mean stability result. Okay, then moving forward, control of active and reactive power. So again, like although already we discussed the control of active and reactive power, and then we concluded that active power control is related to the frequency and speed of the generator. And when load changes or active power demand changes, then frequency change and hence the speed. This thing, that continuously the customers are changing some sort of load, and that might impact the active power, and hence the effect goes on frequency and then the speed. And governor control is used for frequency, speed, and hence the active power. We already covered this thing. And then control of reactive power. So here I have written something: for efficient and reliable operation of power system, control of voltage and reactive power should satisfy the following objectives. And then the main goal is that reactive power control is related to the voltage and power factor. So, I mean, two things. Here, I mean, already I told these things. two things, control of reactive power and then control of the active power. Now, as you can see, the frequency, speed, and then active power, and here I am saying that reactive power, voltage, and power factor, you might see that all are like interrelated. All are interrelated, but still there is some difference. It depends the mode of dominance. It depends on the system structure. For example, if a system has induction machine, or if a system has more wind generator than the synchronous machine, then your order of preference dominating mode will be reactive power control, and hence controlling the voltage and power factor. If your system has synchronous machine, your main goal will be to control the active power and the frequency and then the speed. So this means that typically if you have a synchronous machine, then you have to give preference active power, frequency, and speed. If you have a induction machine, you have to give priority of controlling reactive power, voltage, and power factor. I mean, all are interrelated. I mean, just a moment. Let me take you there. So therefore, if you see this one, I mean, power triangle, you know, that almost every day we are drawing this on, you know, this is P and then this is Q and then this is theta and this is that apparent power. But if you see this picture, then clearly you can see that all three variables are interrelated, right? Because S is root over P square plus Q square. But Q is your reactive power, right? So the Q is your reactive. This is reactive power. But then this one is your active power, or the real power. So we discussed that reactive power control means voltage control and power factor control. We discussed that active power control means frequency control, speed control. But what I am telling that if you see this diagram, this is P, this is Q, and then this is S, and then really that S means, I mean, of course, that vector S means P plus minus and the JQ. This one, when this is real power, this is reactive power, and this is the complex power. Here it is apparent power. So what I am telling that those two are interrelated. Those two are interrelated. I mean, if you, for example, if you see that, okay, I am squeezing, sorry, I am reducing the magnitude of Q, then definitely your triangle is getting changed because your theta is getting changed. P might be the same, but this has been reduced. And then if you reduce the Q, definitely S is getting reduced. Therefore, all three are interrelated. That is fine. But still, the reactive power and then the voltage and then the power factor, these three are the dominating factor in case of the induction machine. So meaning that if it is induction machine, you have to give priority to controlling these three factors. If you don't do that, for example, if it is induction machine, but you are giving priority to control active power or frequency and the speed, then system might come back to stable condition, but still there might be some sort of oscillation. Similarly, for example, your system is synchronous machine and it should be your preference or dominating mode, controlling frequency, speed, and then active power. But you started controlling these things. System might come back to the stable position because of this interrelationship, but might not be appropriate. Still, there could be some sort of oscillations is going on in the system. So do you understand what I am telling? I am telling that this three factor should be controlled if the system has induction meshing. These three factors should be controlled if the system has synchronous meshing. Now what I am telling that, for example, there is a fault and it is a synchronous machine, but instead of these three, I am controlling these three, because that is the thing I am explaining, that you know that it is interrelated. But what happens if it is synchronous machine and instead of controlling these three factors, you only control these three factors, system might come back, but there will be some oscillation. Similarly, if it is induction machine, then instead of controlling these three factors, you first control these three parameters, frequency, speed. Again, system might come back stable, but there will be some sort of oscillation. Therefore, the best approach will be, when it is induction machine, then first control these parameters. Then system will be properly stable. If it is synchronous machine, then you first control these three parameters. Then it will be stable. Sorry. Then the system will be stable. That is the thing I am telling. I mean, it depends on the dominating factor, mode of dominance. So therefore, induction machine is governed by this factor, synchronous machine is governed by this factor. Now, if there is a situation that your system has both synchronous machine plus induction machine, then you have to control all 6 variables: reactive power, voltage, power factor, frequency, speed, and the active power. So therefore, depending on the system, if the system has a mixture of synchronous machine and induction machine, then you have to make sure that, okay, you are controlling all 6 parameters to properly maintain the stability. Only one set is not enough. So everybody, could you follow me what I am saying?
Yes, Dr.
Yes,
Ali.
Dr. Ali.
Yeah. Therefore, I mean, why I am telling these things now, if you read many literature and like others research, or you are listening to someone's lecture or in a conference paper, that will help you. If you could just remember these things, that why on journal paper is discussing these things when dealing with induction machine or the wind generator, why the paper is giving emphasis on these factors when dealing with synchronous generator. That time it will help you to understand. Okay, so then moving forward, I think we don't have much time. So you understood these things, and then I think at last there was a numerical problem. Everybody read the problem. We might not have time to solve today, but you can try. Everybody read the problem. A 3-phase 600 MVA 2-pole 60 Hz synchronous generator as shown in the following figure. I have drawn the figure, I mean in the PowerPoint using the pencil. Has a rated current 160 kiloampere and feeds via on is to 2 transformer, a 3-phase 750 horsepower Y connected induction motor that has a full load efficiency of 90% and a lagging power factor of 0.75. Now, to improve the power quality of such a load, a capacitor is connected at the load terminal that ultimately makes the power factor 0.85 lagging. What is the value of reactive power provided by the capacitor? Also, what is the motor terminal voltage? Therefore, you see, I have drawn this picture for you. This is a synchronous generator on the very first line. It has 60 MVA capacity. Its current rating is 160 kiloampere. And through a transformer, it is powering the induction motor. That induction motor has 750 horsepower rating and its efficiency is 90%. And the turn ratio, this side is 2, this side is 1. This means this side has twice number of turns as compared to the left side. So based on that, what is the statement says? A capacitor is connected at the terminal. That ultimately makes the power factor 0.85 lagging. So meaning that initially the power factor was 0.75, and then capacitor made the power factor changed, increased. It's still lagging, but improved 0.85. So what should be the value of the reactive power that has been provided by the capacitor? Here, at the terminal here, you connected a capacitor to increase the power factor. And also, what is the value of the voltage here? Voltage is not given neither this side nor that side. But I am asking, what is the voltage here? So now by using this information, this is MVA 160 kiloampere, you should be able to find out the voltage. What is the voltage here? That is the question. And what should be the reactive power that is provided by the capacitor? You have to utilize this information. So everybody, do you understand this one?
Yes, Dr. Ali.
Yes. So therefore today there is not much time. So please you try at home this one. And then next class you let me know that what result you got. And there will be two answers. One is the motor terminal voltage, and then the other one is what is the reactive power that will be provided by the capacitor. Capacitor will be connected in parallel here, parallel to the induction motor. So please try your best. Okay, so do you have any questions, comments?